All right, guys, in this lesson, we're going to be studying statics. Statics refer to forces that are acting on an object, but that the object is not in motion. And that's why we use the word statics, because although forces can cause motion, they can cause acceleration, it's also possible that they wouldn't. So there are lots of things that are, for instance, sitting still but have plenty of forces on them, and that's the study of statics. There's so much to learn about them, including just some straight up vocabulary like concurrent forces, but also lots of skills like the resolution of forces, and we'll talk about equilibrium a bit as well. There is a homework, of course, associated with this. It looks like it's not super long, questions 41 to 54 on pages 37, 38, but we'll do that in class. And take a moment now and pause the video. I really want you to read through these do not questions and think about what your answers would be for each. So let's say that you're sitting in your chair and you have a bunch of forces acting on you. You have forces including gravity, which is down. You have a normal force. And the normal force is the force that is opposite of gravity. It's going to go up, and it's provided by your chair. And then I guess you could also say there's air pressure forces, which are coming from all sides, so every direction. It's hard to even say like what arrows I should draw there. I'll just put in several arrows that are sort of pointing towards the middle. Now, if I draw a diagram of you in your chair with all the forces acting on you, let's say here's the chair. It's a side view. And let's say that you are a red stick figure with your hands in the air. Okay, the forces that are acting on you primarily are, starting from the center, and the one going down is going to be gravity. And the one going up, which hopefully is equal and opposite, is going to be the normal force, which is Fn. I'm going to try that again. Fn. So we have a normal force going up and a gravitational force going down. And the net force acting on you would have to be 0 newtons. And that's the evidence here is that you are not accelerating. So if you're sitting in your chair very peacefully right now, then you can rest assured that all the forces that are acting on you are balanced. Okay, so concurrent forces. Concurrent forces are forces that are, let's say, more than one force, and they're acting on the same object. There are lots of things that you need to know about them, but I think that the really to the point part of it is that if you have two forces acting on the same object and they're acting in a line, so they're in the same direction basically, then you can add them together or you can subtract them just using regular algebra to figure out the force on that object. So for instance, we have this object P, and it has an 8 Newton force moving to the right, and it also has a 6 Newton force moving to the right. What you can do, I'm just going to highlight the 8 Newton one and also highlight it over there, and then I'll highlight the 6 Newton one and also highlight it over here. So what you can do is you can just add them together to get a total, like, overall resultant force of 14 newtons. So there was a new vocabulary word I just used. It was the word resultant, and it's down here, R equals 14 newtons. I just added those two together because they're in the same direction anyway. And then this is sort of the same idea, but now they're in opposite directions, but they're still in the same line. And I'm just saying, like, you have an 8 Newton force to the left, and here it is as well in red. And we also have a 6 Newton force to the right, and there it is as well. So one of the things I did, I don't want you to miss it, is that the here's the head of one vector, and here's the tail of the other. So I am doing a head to tail method. It's listed right here, but there's the head and there's the tail. So you always line up the tail of one vector with the head of the other. But you come out with this as a difference. So the difference between the two vectors is it looks like only 2 newtons. And that 2 Newton force is primarily pointing to the left. So that means that the resultant force in this case is 2 newtons left. So as a quick overview for this slide, we learned the word resultant. Resultant is when you combine 2 forces to make one force. And we also learned the word concurrent forces. Concurrent forces are more than one force acting on the same object at the same time. And what we did down here as an example was an example of the maximum resultant force and the minimum resultant force for 2 objects. So the maximum resultant force is pictured here, and the maximum was 14. And what you should write down in your Cornell notes right now is that the maximum resultant force is always going to occur when you add the 2 forces together because they're in the same direction. And here, the 2 newtons force to the left, that was the minimum resultant force. And what you should write down is that the minimum resultant force always occurs when you subtract the concurrent forces, so 8 minus 6, and you're subtracting them because they're in opposite directions. So it looks like, and this is my sort of simple way of putting it, if you have 2 forces of 6 newtons and 8 newtons, the minimum force you could have between those 2 is 2 newtons because I subtracted. And the maximum force you can have between those 2 is 14 newtons because I added. So you could never have less than 2 and you could never have more than 14. That's the big ticket I think that's going to help you a lot in the future, is that if you have a 6 Newton and an 8 Newton concurrent force, the minimum resultant force is 2. You can't have less than that. And the maximum resultant force is 14. You cannot have more than that. I think the amount of notes you need to write for this slide is really minimal because we will have done some practice in class on how to do these already. But you know what you should write down is that when you have a couple of forces, we'll just say F1 and F2, and they're acting concurrently on some point, that you can use the head to tail method for drawing the resultant vectors. So just make sure that you draw one vector with the correct angle and the correct size. So like here's F1 and there's F1 again. But when I go in to draw F2, just make sure that you draw the tail of F2 at the head of F1. So instead of drawing it down here at P where the tail of F1 is, take the tail of F2 and move it up so that it's on the head of F1. So it'll still have the same angle and the same size, but it'll be in a place that you might not expect. So it's a head to tail of the next vector. So the head of the first vector to the tail of the second. Keep the angle correct, and then you'll just go up and out like that, and then the resultant is that guy going from start to finish. Same idea here, 2 forces, F3 and F4. When you draw them, just make sure that, I guess we'll say F3 is our first one, so here's F3, right there. Same magnitude, same direction, but then F4, I pick it up and I move it up there so that the tail of F4 is at the head of F3. So here's the tail of F4 at the head of F3. It's right there, and it changes sort of the way it looks. So there's F4, and then the resultant is that guy. You can do this with 3 vectors as well if you want an extra challenge. So starting with F5, and then F6, and then F7. So here's F5, and then F6, same angle, same size. It's just that I picked it up and moved the tail to the head of F5. So the tail of F6 to the head of F5. And that would mean that the tail of F7 needs to go on the head of F6. So here's the tail of f7 on the head of f6, and the resultant is the same, just from the beginning to the last vector. That's the resultant. All right, so when we're finding the resultant, if let's say that you have a 90-degree angle, like in this guy, one of the things I would really recommend is not solving it graphically, but just by using trigonometry, or in this case, the Pythagorean theorem. So like this guy, it's a 6 and an 8 are the two legs, and you want to solve for r. Here's the Pythagorean theorem. It says a squared plus b squared equals c squared. I want you guys to pause the video now and use the Pythagorean theorem to solve for the length of r. So I used the Pythagorean theory to figure out at least the magnitude of this resultant. I used a squared plus b squared equals c squared. I rearranged so that c is a squared plus b squared. I'm just calling that guy c. And then I had 36 plus 64, and I got is square root of 100, and then 10 newtons was my final answer. I do need to solve for the angle as well, because I said to solve for the resultant, so probably I should do the angle as well. I think that you could use sine, cosine, or tangent here, but I'm going to recommend tangent because it would be using the opposite side and the adjacent side, neither of which were things I solved for. So, which is good. So I'll set that up now, and then you can pause the video and solve from there. So the equation that I know that you can use for tangent says that the tangent of theta is going to be side A over side B. And side A is going to be 6 newtons, and side B is 8 newtons. So the tangent of theta is that guy. So solve for that right now. My big hint for you is that you'll need an inverse tangent to get the final answer. Okay, so I used an inverse tangent function to take my ratio of 6 to 8 into an angle, a degrees angle that made sense. And I went ahead and put this into, I said north of east. It's a really important thing to add because I am referring to this angle, just by the way. So this is the 37. But 37 could be really in any direction. So the way that you're specific is that you define it in terms of 2 directions. So if this is east, straight out to the right, then 37 degrees above that, or 37 degrees to the north of east, is the angle that I'm actually looking for. So you start out at east, and then you go 37 degrees north, and then that's your angle. So that's why I said north of east. All right, so aside from the head-to-tail method for adding concurrent forces to find a resultant, there is another method that I have to mention, even though I never use it. It's really not my favorite thing. It's called the parallelogram method, and it's different than head-to-tail because you don't draw the tail of the second vector against the head of the first vector. Instead, what you do is you draw all the tails of the vectors together. There really can only be 2, I think. But you draw the 2 tails together. So in this case, it looks like we're doing force vector F1, and we're combining it with force vector F2. But as you can see, the tails are together down here instead of head to tail. And what you do is you take those 2 force vectors, and you convert them into parallelograms, actually. So I'm going to draw a parallel line to force vector F1, and it's going to be right here. I'm just doing dotted line because it's like the parallel line. And I'm going to draw a parallel line to force vector F2. Now, the place where they connect, those 2 parallel lines, that's going to be like your end point or the stopping point. So what you do to find the resultant is you go from the beginning where the 2 tails were meeting and all the way to the end where the 2 heads of the 2 parallel lines meet, and that will be your resultant. You can, if you've scaled it correctly, you can just use your metric ruler to measure that, and you can use a protractor to measure that angle, and then you can easily find your graphical answer. Some of this weird language you see down here about 0 degrees and 180 degrees is telling you about minimum and maximum resultant forces. Just know that when you have two forces that are lined up like this blue one and this green one, they're at an angle of 0 degrees with each other. And 0 degrees means basically that you're parallel and in the same direction. And that's when you're going to have your maximum resultant force. So in this case, it's going to be 8 plus 6 is 14. We did do this on a previous slide, by the way. And your minimum force is when they're at 180 degrees, when they would still be lined up in the same line, but they would be pointing in opposite directions, and that's when you would subtract them, and that would be the minimum force, and I think in this case it would be 2 newtons. So this slide is, in a lot of ways, a slide of opposites. Because in the previous part of this lecture, we were talking about adding force vectors together to get a resultant. And you could do that graphically, you could do it algebraically, trigonometrically, but there is sort of the opposite of that, which is to take a single vector, which you could think of as a resultant, and break it up into its components. So instead of being, one vector, it really could be any number of vectors, to be honest. But the by far the most useful thing we can do is to break it up into 2 vectors that are perpendicular to each other. Because if you do that, you get to use all of trigonometry it's all at your advantage there if you have a right angle. So yeah, this slide is just introducing that idea that you could take, for instance, this vector right here. You could think of it as a vector, and you could break it up into 2 perpendicular components, maybe a vertical component and a horizontal component. So this is the resultant, and then a vertical and a horizontal. So this, I guess, would be the same diagram, just divorced of all puppies and leashes and stuff. Yeah, so I think main things to write down are that you can take a resultant and split it up into components, that you could really have any number of components, but we typically only do 2, and they're perpendicular. The information on this slide, I think, is some of my favorite in this lesson, because you have 2 things that are both on your reference table, and they're extremely useful. So the algebraic way of taking a resultant like vector A and splitting it or resolving it into its components, such as we call that one AX, and we can call that one AY, and we can call this one AX, is just these little formulas right here. The one that says AX equals A cosine theta and AY equals A sine theta. Both of these are on your reference table. I believe they're on the back page, maybe a third of the way down or so. They're away from the trigonometry section, which is interesting. But it's helpful because at least it's there and you can use it. So don't forget about these. These are awesome. And they're both just based on the standard equations that you would find under the geometry and trigonometry section of your reference table. Basically, it's just a little bit rearranged, and I'm using different symbols instead of the typical ones. But if you try to isolate cosine theta, for instance, and then you would divide both sides by a, and you would get the cosine of theta is equal to ax over a. Now, ax is really what we would call the adjacent side, and in your reference table, I believe they call it side B. And side A is what we would call the hypotenuse, but I think your reference table calls it side C. So this equation is really just saying that cosine of theta is B over C, which you can find on your reference table. And then, similarly, AY equals A sine theta. It would come out to say that sine theta is equal to AY over A. AY being side A, and, well, lowercase a, and then uppercase A is side C. So that's just the equation that you would already find for sine theta on your reference table. So this is how we take one vector and split it into its components, is we just use the angle theta, and we're able to figure out side A and side C. But this equation is really, really great to figure out the horizontal component primarily, and then this one is to figure out the vertical component. This slide is just an algebraic resolution of this force right here on the puppy, and it's an algebraic resolution of that single force into two forces, a horizontal and a vertical one. I am basically using the equations that were on the previous slide. I'll write them in now. So here are those equations, AY equals A sine theta and AX equals A cosine theta. You can see really easily how this all lines up. So AY is the vertical force that I'm looking for. So we can call this one AY. And AX is the horizontal force, so I'll call this one AX. And yeah, it's all basically laid out here. It says that the vertical force is A sine theta, which is just straight from the reference table, and this is A right here, and then sine of theta would be sine of 40, so I'm just going to write 60 sine 40, and it'll immediately solve down to 38.x. You don't need to use inverse sine, you just use normal sine. It's so easy, it's like the best equation. I use it all the time. Over here, if I want to look for the horizontal component of the puppy's leash, then I just use AX equals A cosine theta, where AX is the horizontal component, A is the hypotenuse, and then cosine theta is going to be cosine of 40, and it just says 60 cosine 40, and it solves down to 45.9. Again, extremely simple. Just, I guess, try to remember that if you have this vector, if you have a vector, you can easily solve for the vertical and the horizontal components by just using the equations on your reference table on the back page. AY equals A sine theta and AX equals A cosine theta. Okay, so I have two questions here that'll help us practice these concepts. The first one is basically that you're a person and you're pushing a lawnmower. But what happens when you change this angle? So like what happens to the horizontal component? What happens to the vertical component as this angle changes, as it goes up or as it goes down? That'll have different effects on the components. Now, in short, if I move this handle down towards the ground and push with the same force, it'll actually be a stronger horizontal component, and it'll be a weaker vertical component. I'm going to draw something in, and then I'll draw something else to compare it to. Okay, so I just drew a red triangle here. Basically, the hypotenuse is the force F, and then this leg is the horizontal force, and that leg is the vertical force. I'm going to draw a similar triangle in black, but in that triangle it'll have a larger angle. I did my best to keep the hypotenuse, I know it's mangled, but I did my best to keep the hypotenuse the same length as this hypotenuse, so they should be similar in length. But by changing the angle theta, which is right there, I was able to really accentuate the vertical component, and I was able to sort of reduce the horizontal component. And I'll do one more triangle in blue that'll represent what happens when you lower the angle. Again, I really tried to keep this hypotenuse the same length as that hypotenuse, and that made the horizontal component of the force larger than the horizontal component at normal angle theta, and it made the vertical component smaller. So again, what happens is when you increase the angle, the vertical component increases, and when you decrease the angle, the vertical component decreases. Or when you increase the angle, the horizontal component decreases, and when you decrease the angle, the horizontal component increases. This is just my shorthand way of saying that. And in the next question, it has this very oddly dressed man. I don't know if he's a gravedigger or exactly what's going on, but he's exerting 300 newtons of force along this vector towards the ground, and the angle that the shovel is making with the ground is 60 degrees. Specifically, this question asks me to calculate the magnitude of the component of the force which is perpendicular to the ground. So they're really only asking me to solve for AY, but I'm an overachiever, so I'm going to solve for AX as well, but I'll do it second. So if I'm solving for AY, which would be this vector right there, I'm going to use that equation that I was telling you is one of my favorites. It just says AY is A sine theta. It's really easy to use. So it turns out AY is going to be 300, which is the value for A, and sine of 60. So I'll calculate that and I'll put the answer in. My calculator gave me a value of, I guess we'll round that. Yeah, it's going to be 260 decimal newtons. Now, if I wanted to do this for AY, it would be AX, it would be so similar, except I would use the equation AX as A cosine theta, but a lot of the values would be the same, so A is still going to be 300, and I'm going to multiply that by cosine of 60, so I'd still use the same angle, but I'm going to use cosine, and the answer for that is, I got 141 newtons. Just bear in mind 141 newtons is a bit smaller than this 260 newtons up here. And that's okay, because the man, you can see by the angle of 60 that he is exerting most of his force along the vertical section, which is why AY is 260. And he's really doing a lot less of his force along this horizontal section at the bottom. He's only doing 141. And I also want to point out that 260 plus 141 is not 300, which is, his overall force. Basically, it's kind of the same thing that you would do in geometry, where in order for it to be a triangle, I think it's the sum of side A and the sum of side B have to be greater than the sum of side C. And this is side C, and the sum of A and B have to be larger than C in order for it to be a triangle. So this slide has a really short discussion on equilibrium, which is that if you can get all the forces acting on an object, all the concurrent forces, to sum up, whether that's algebraically or whether that's geometrically, if you can get them to sum to zero, then we say that that has a net force of 0 newtons. Another interesting thing, if you can say that the F net is 0, then you can also say that the acceleration will be 0, and I guess meters per second squared, I should add. And that's because of the equation on your reference table that says that F net equals ma. So if you can say that F net is 0, then acceleration has to be 0. So anyway, the rest of this slide is just saying that all those forces add up to 0 if the object is in equilibrium. And they use an example of a sign hanging from a building like that. And that there's a force along the cable that goes both up vertically and also horizontally, because it's sort of going up in the air in both directions. And you also have a support rod, which keeps the sign from swinging into the building. So the support rod pushes out. And the sign itself has its own force, which is its weight. and that's going to pull down. So you have three forces, this one, and this one. And just for convenience, since these two are already perpendicular, you can take this one and you can split it into a vertical as well as a horizontal component. And what you'll notice is that they graphically add to 0 if the object is in equilibrium, meaning that the forces can cancel each other to produce a 0 force. So I will copy this pair up in this summary for you, and I'll photocopy it so you'll have it to work on in class. But just pause the video and read through the problems so that you have a really good idea of what you're being asked to do, even if you don't have a solution for it yet. And this is a continuation of that same pair up.